There are four aspects of radiation to consider. There are two types of radiation, ionizing and non-ionizing. Examples of ionizing radiation include alpha particles, beta particles, X-rays, and gamma rays, all of which are harmful and measured as an absorbed dose by the unit joule per kilogram (JkG). In physics, 1 joule per kilogram is called a gray (GY). Outside of the Earth's atmosphere, astronauts need protection from ionizing radiation in low Earth orbit and beyond. This becomes even more important for astronauts as they venture beyond low Earth orbit and Earth's protective magnetic field. B. Equivalent dose. Since there are different types of radiation, there needs to be a further method of determining its biological effects. Proponents of the Apollo missions say that alpha radiation in the outer regions of the Van Allen belts can easily be stopped with a few centimeters of air or paper, while beta radiation can be stopped with aluminum, thus giving the impression that manned missions through this region would cause little or no harm to the astronauts as long as they traveled through this area quickly. This is partially correct. However, as this chapter will show, NASA is not sure of the energy levels in this region of space around the Earth, and if alpha particles are inhaled or ingested, they could be the most destructive form of ionizing radiation. Given that alpha and beta radiation will have different biological effects, a numerical quality factor Q between 1 and 20 is used to determine the equivalent dose. Alpha particles are given a Q factor of 20 since it causes more harmful biological effects once ingested. Beta and gamma radiation are assigned a Q factor of 1. Alpha and beta are forms of particle radiation that are relatively easy to stop. Even though gamma radiation is assigned the lowest Q factor, it can be the most penetrating, causing enormous harm to astronauts depending on its energy. Therefore, 1 GY of alpha radiation is 20 times more harmful than 1 GY of beta or gamma radiation. The sievert, SV, which is the International Unit System, SI, is used to interpret the varying biological effects from different types of radiation. For reference purposes, 1 GY of alpha radiation is an equivalent dose of 20 SV. 1 GY of beta radiation is an equivalent dose of 1 SV. 1 GY of gamma radiation is an equivalent dose of 1 SV. Other types of radiation are given different Q factors between 1 and 20. Effective dose. Since different types of radiation can strike different parts of the body, a new quantity called the effective dose is used in which each organ or part of the body is assigned its own Q factor. This is one of many factors considered when designing spacecraft shielding. The figures used above in equivalent dose are further broken down into millisieverts, MSV, or 1 sievert is equal to 1000 millisieverts. It is the millisievert that is usually used in determining the effective dose for individuals. And when using figures such as 0.1 millisieverts or 1 sievert, you still use the Q factors 1 to 20 to multiply them. Dose rate. A dosimeter is used to measure the dose rate, usually in millisieverts per hour. The Apollo astronauts were supposed to have carried a dosimeter on board. Although average dose rates for the Apollo astronauts have been released, individual dose rates remain classified. The RAD and the REM. The absorbed dose was referred to as the RAD, while the equivalent dose was referred to as the REM. Thus, these are old terms which now have been replaced by the GY and SV. The average yearly dose per person in background and man-made radiation in the United States is approximately 0.62 rems, which is 620 mrems, or as expressed in the new unit, 0.0062 sieverts, or 6.2 millisieverts. Many of the science and engineering books I've referred to have used the old term of rems. I'll refer to this term and use 0.62 rems as the approximate average per person yearly dose in the United States as a reference point when discussing attenuation of radiation and how many rems astronauts could have been exposed to. There are many online conversion tables that can be used to convert rems to sieverts if necessary. I hope this brief description will help you in your research into the Apollo moon missions when reading about shielding and attenuation of radiation, which will be discussed further. Van Allen radiation belts. The Van Allen radiation belts are two regions of energetic particles that encircle the Earth, excluding the north and south polar regions. Any manned mission to the moon would have required a trajectory through the radiation belts, which NASA claims is safe for astronauts as long as they have proper shielding as they travel through the outer regions of the outer radiation belt quickly, therefore minimizing radiation exposure. Discovery of the Van Allen belts. In 1958, Dr. James Van Allen discovered two radiation belts surrounding the Earth through two unmanned missions. Explorer 1 launched February 1, 1958, and Explorer 3 launched March 26, 1958. The inner and outer radiation belts consist of energetic charged particles, the inner belt consisting predominantly of protons and the outer belt of electrons. Dr. James Van Allen writes, "The inner belt reaches its peak at about 2,000 miles from the Earth, the outer one at about 10,000 miles. Beyond 10,000 miles, the radiation intensely diminishes steadily. It disappears almost completely beyond 40,000 miles. The maximum intensity of radiation in each belt is about 25,000 counts per second, equivalent to some 40,000 particles per square centimeter per second. The maximum intensity of radiation in each belt is about 25,000 counts per second, equivalent to some 40,000 particles per square centimeter per second. Solar wind is tenuous ionized gas called plasma and is the main source of energetic charged particles in the radiation belts. The solar wind, or ionized gas, encounters the Earth's magnetic field by first hitting the magnetosheath, which is often referred to as the bow shock. This area extends approximately 37,000 miles from Earth. Below the magnetosheath is the magnetopause, and below that is the magnetosphere. From here, these charged particles in the magnetosphere, mainly protons and electrons, are trapped inside Earth's magnetic field. Within Earth's magnetic field, these charged particles are now influenced by Earth's magnetic north and south poles, traveling along magnetic field lines. Hence, the Van Allen belts are in constant flux and form one of the many pertinent factors to consider when sending manned missions through this area. Conflicting information regarding intensity of Van Allen belts. People who question the Apollo missions are usually referred to as conspiracy theorists. This term was invented by the CIA to dispel any rumors of conspiracy regarding the JFK assassination. Further, conspiracy theorists are often accused of quote mining. It is another term used in an attempt to further discredit anyone writing about this subject. Quotes are used by authors at the time, and I will use them in this chapter to show the discrepancies and conflicting information regarding the Van Allen belts. We'll start with the conflicting information regarding the size and energy levels of the radiation belts, as is presented in numerous books and articles. Here are several points taken from 6 sources that show the discrepancies and conflicting information regarding the Van Allen belts. After each source, I offer my analysis. 1. Dark Moon and the Whistleblowers by Mary Bennett and David S. Percy. In Spaceflight and Rocketry, a chronology, David Baker has an entry dated March 20th, 1959 for an announcement of further radiation belt data from Professor James Van Allen, stating that the inner belt extended from 1,500 to 3,000 miles, the upper belt from 8,000 to 55,000 miles. Yet the same year, in the highly respected Scientific American, James Van Allen states that the radiation zones extend to 64,000 miles. In 1997, websites quoted the starting point of the Van Allen belts at between 250 and 750 miles from Earth, hardly a starting point and more of a vague zone. Also in 1997, British university students were also informed that the Van Allen belts extended from 621 to 3,107 miles for the lower belt, and the upper belt only continues to a mere 12,430 miles. The above distance is even more astonishing, with the upper belt apparently ending 51,570 miles short of Van Allen's own data. As this list compiled by Bennett and Percy shows, there are several different interpretations of the data. It would provide some clarifications if the scientific community could at least agree on where the radiation belts start and where they finish, considering the solar wind that extends the Earth's magnetic field on the side away from the Sun. In any manned space mission, an absence of precise data as to the extent of the radiation belts means that an exact length of time which is safe for astronauts to be exposed to radiation can't be determined. Radiation and the International Space Station recommendations to reduce risk by Space Studies Board, Board of Atmospheric Sciences and Climate, National Research Council says, one component of the belts, the outer belt, MeV electrons, has long been known to be highly variable. Flux frequencies vary by several orders of magnitude, with an interval of high flux observed typically once a month. Though MEV electrons rarely penetrate into the interior of a spacecraft, they can be hazardous to astronauts performing EVAs. Most other components of the belts, including highly penetrating energetic protons, are generally much more stable and predictable. However, we now know that stability is not absolute. The actual data for outer electron flux is not defined in their text. Does this mean that there's a possibility that several orders of magnitude of MEV electrons have the potential of penetrating a spacecraft shielding, posing a risk to astronauts? Yes, it does, and their quote, MEV electrons rarely penetrate into the interior of spacecraft means that they penetrate given the magnitude of the flux. The information from the second source above is a contradiction in terms and particularly significant as it will be seen next. Space Radiation Hazards and the Vision of Space Exploration report of a workshop by National Research Council of the National Academies. The region of trapped radiation within Earth's magnetosphere consists of energetic protons, electrons, and heavy ions organized in two belts, a relatively stable proton-dominated inner belt and a highly variable electron-dominated outer belt. Energies range from approximately 10 keV to greater than 400 MeV for protons and from tens of keVs to greater than 10 MeVs for electrons. Manned missions in geospace are flown in low Earth orbit at altitudes below the inner belt. However, astronauts embarking or returning from journeys to the Moon or Mars will have to pass through the Van Allen belts and will be exposed for brief periods of high levels of radiation. We just learned from the National Research Council's previous quote from Source 2 that the inner proton belt stability is not absolute. Yet, in the quote just above from Source 3, they're now saying that the inner proton belt is relatively stable, therefore insinuating that it's now absolute. This is a major contradiction. It would also help to know what the intensity of these high levels of radiation are, as they would have to have been determined during the Apollo missions 50 years ago. But decades later, they are now questioning radiation intensity in this region. So, either NASA has lost this data, or they never had it to begin with. How Apollo Flew to the Moon by David W. Woods. For a few minutes, as they raced away at 10 kilometers per second, the crew passed through the Van Allen belts where they received a small dose of radiation. This is an inner torus populated by energetic protons which the spacecraft passed through in a matter of minutes and against which the spacecraft's skin was an effective shield. The spacecraft took about an hour and a half to traverse the more extensive outer torus, but this region has mainly low energy electrons and so was less of a worry to mission planners. Notice how W. David Woods quickly skims over the issue of attenuation of radiation with his phrase, "The spacecraft's skin was an effective shield." This quote also represents more conflicting information regarding how long each Apollo mission would have taken to travel through the Van Allen belts. As to how long the Apollo missions were in their radiation belts depends on the source, as I have read several estimates, none of which seem to agree. The graph below shows different estimates by varying groups as to how long the Apollo missions were in these regions of the Van Allen belts. On a matter as important as this, all sources should agree, and as is evident, they don't. Dr. James Van Allen in Scientific America, March 1959. Unless some practical way can be found to shield space travelers against the effects of radiation, manned space rockets can best take off through the radiation-free zone over the poles. This is interesting since the discoverer of the radiation belts, Dr. James Van Allen, has said that manned missions should travel in an area through the north or south poles, which there is little or no radiation. Near the end of this chapter, you'll see why it took Dr. Van Allen over 30 years to refute his own statement about manned missions safely traveling through outer regions of the Van Allen belts besides the radiation-free zones. An Introduction to Space Travel by Mark Moldwin. The radiation belts contain intense radiation that can kill astronauts and damage or destroy sensitive electronics on spacecraft. Understanding this region is one of the main efforts of space weather, since many important satellites have their jobs in or through the radiation belts. NASA recently posted a YouTube video with one of its engineers, Kelly Smith, talking about the intensity of the radiation belts and the need to solve numerous problems before sending manned missions through them. Proponents say that the intensity of the radiation belts Kelly Smith is talking about only applies to sensitive modern electronic equipment on board new spacecraft. Mark Moldwin's above quote shows that's partially true, but radiation intense enough to harm sensitive electronics can also harm or kill the astronauts. Smith completely ignores the Apollo mission's travel through the outer regions of the radiation belts, and he doesn't specifically say in the video where those radiation intensities are. Hence, the inference is, it's not safe for manned missions no matter what area of the radiation belts these missions attempt to go through, and that's with 21st century technology. Note, with the exception of Dr. James Van Allen, all above quotes come from sources decades after the Apollo missions. There's one more thing to add here, and that's the variation in the Earth's magnetic field over the South Atlantic. It's the area of the Van Allen belts that dips to an approximate altitude of 100 miles over Brazil and stretches out over the South Atlantic Ocean, commonly referred to as the South Atlantic Anomaly, SAA. Special precautions aboard the International Space Station, ISS, need to be taken whenever traveling through this region because of intense proton radiation, while on the other hand, all Apollo manned missions spent 10 to 15 minutes traveling through this inner belt with no apparent health effects on the astronauts. This presents more conflicting information from NASA. Outer electron belt would have exceeded Apollo spacecraft shielding. In this section, we'll use the terms KeV, MeV, and GeV. KeV, kilo electron volt, which is 1000 electron volts, MeV, mega electron volt, which is 1 million electron volts, and GeV, giga electron volt, which is 1 billion electron volts. A reference point to remember for the Apollo missions is that the attenuation of radiation up to 14.7 MeV electrons in the predominantly electron outer Van Allen belt. Being exposed to high levels of radiation for short periods of time is tolerable, but of course, you want to know what the energy flux of these high levels of radiation are. The Proton AP and Electron AE8 radiation belt models of 1976 say that electron energies are no greater than 7 MeV in the outer Van Allen belt. Yet, as was mentioned above, the National Research Council published its report in 2006 and said electron energies are greater than 10 MeV. However, in their 2008 publication, the National Research Council refers back to the AP8 and AE8 models of 1976. It states, the trapped particle models in current use are the AP8 for protons and the AE8 for electrons, Sawyer and Vette, 1976. Although the AP8 and AE8 models are still widely used for spacecraft design, it is recognized that they are severely outdated because of the secular changes in Earth's magnetic field since the era when measurements underlying the models were made. It is now recognized that radiation belts vary on timescales shorter than just the solar maximum, solar minimum levels described in the AP8, AE8 models. Example, Blake ETAL 1992, LIETAL 1993. NASA's Living with the Star program's radiation belt storm probes, which are scheduled for launch in 2012, are expected to provide measurements that will be the basis for new models. In the meantime, there are also efforts aimed at extending the capabilities of existing models and improving their accuracy through reanalysis of existing datasets. Beta version of new models, designated AP9 and AE9, are scheduled for release in 2009 to 2010 timeframe. Efforts at improving models for Earth's trapped radiation are important for other NASA missions, as well as the DoD and for commercial use of space. Now we're back to the Van Allen belts with electrons no greater than 7 MeV. So which is it? 7 MeV electrons or greater than 10 MeV electrons? Since the National Research Council says that there are electrons greater than 10 MeVs, how high do these electron energy fluxes go? This is the most important question of all, since NASA claims the Apollo spacecraft shielding can stop electrons up to 14.7 MeVs, the reference point mentioned above. The 1976 AP8, AE8 radiation belt models have been used by proponents of the Apollo missions in an attempt to prove that the Van Allen belts were safe for manned missions to travel through using the method NASA claimed. Decades ago, NASA was confident in its technology to send manned missions through the Van Allen belts. However, it now seems that NASA and scientists in general are more perplexed about the Van Allen belts than ever before. This is disturbing since spacecraft shielding design based on the AP8 and AE8 models, which now conflicts with the National Research Council's estimates. And with the new AP9 and AE9 models, NASA still doesn't know how high the electron energy fluxes are, which is discussed in detail next. Clash of the Titans. A well-known Australian researcher by the name of Gerard White has been questioning the validity of the Apollo missions for years through his excellent videos, which you'll find on his YouTube channel. He has raised some very interesting but disturbing questions about the Apollo missions that NASA refuses to answer. However, NASA is not without its defenders. One of these defenders is Robert A. Browning, who got into a very interesting and revealing, albeit indirect, online discussion with Gerard White. Browning published an online article in which he attempts to counter conspiracy theorists regarding claims that the Van Allen belts are harmful to any manned mission attempting to travel through them, including the outer Van Allen belt. Note: Browning claims to be a civil engineer and an average person fascinated by rocketry and spaceflight. You can research his article online by typing his name in along with Van Allen belts, and you can check out his other work at www.browning.us. Browning, in his article, shows the actual supposed trajectory through the outer regions of the outer radiation belt. Using mathematics, he explains that given the right method of spacecraft shielding, as is claimed by NASA, the Apollo missions could have safely traveled through the outer regions of this belt. His basis for this data is the 1976 AP8 AEE8 model of the Van Allen belts. When you read through all of the mathematics, you realize that he's using estimates to formulate his own theoretical model. There is no real-time data for the Apollo missions in Browning's article regarding the regions of the outer Van Allen belts, which we'll soon see. His data conflicts with that of the other scientists involved in researching the Van Allen belts. Gerard White counters Browning's online paper with his own use of mathematics, although it is a source of his data that is most interesting. In his YouTube video, Radiation Reloaded, White discusses the data regarding the Van Allen belts, focusing on the trajectory of the Apollo missions. 24 minutes into the video, he specifically counters Browning's claims that White's previous YouTube video, he had used erroneous data to prove that the outer Van Allen belt would have been dangerous for any manned mission. While Gerard White was researching for a university assignment, he came upon a credible source. In an article by Herbert O. Funston and his team from the Los Alamos National Laboratory published on March the 8th, 2013, Funston talks about penetrating radiation, saying electron fluxes are typically observed at energies greater than 15 MeV in both radiation belts, with inner belt proton energies that can exceed 100 MeV. According to the published reports by the National Research Council in the year 2000 to 2008, energies greater than 30 MeV protons can penetrate the mid-deck of the Soviet shuttle. Hence, one should assume that the Apollo spacecraft would be no different. This is interesting considering NASA's claims that the Apollo spacecraft shielding was enough to stop up to 14.7 MeV electrons. White contacted Funston and asked him to quantify the fluxes of the electrons. Funston referred White to one of the authors of the article, a space physicist, Dr. Jeffrey D. Reeves. In his correspondence with White, Reeves, a world expert on the subject, made a startling statement. I've reproduced it here in its entirety from Gerard White's YouTube video, Radiation Reloaded, to avoid misrepresentation. Dr. Jeffrey D. Reeves: the answer is we don't know. Most places in the magnetosphere, there are no electrons with energies greater than 1 MeV. They just don't stick around long enough. In the inner magnetosphere, they can be trapped for a long time. Trapping in the inner belt is much longer than trapping in the outer belt, so the fluxes greater than 10 MeV electrons tend to be higher and steadier in the inner belt. How high and how steady, I'm not sure. Here's why. 1. You need a really large detector to measure greater than 15 mega-electron volts. Larger means heavier, so we typically don't fly detectors that are massive. The measurements we do have are typically inferred from backgrounds in detectors that are intended for other purposes and for which the electron response sensitivity is not well known. 2. Integral measurements like Van Allen's Geiger tubes can tell you the total counting vote of electrons that trigger a response in the detector, but the sensitivity as a function of energy is not well known. It's an integral measurement, but for some point, the sensitivity falls off. For instance, when an electron passes through a detector, it will only deposit part of its energy. 3. Bremsstrahlung. Any material around the detector will produce X-rays when hit by very energetic electrons. Those X-rays will often also be measured by the detector, but now the collecting area you assume isn't the entrance to the detector, it's the whole spacecraft. It is for these reasons that the AE-8 only goes to 7 MeV. You will either have to extrapolate the spectrum and integrate it numerically, or you will have to dig into the original literature and look into both measurements and the caveats. I'm sorry, I just can't give you the answer. For the purpose of our study, designing a detector that properly measures greater than 50 keV and ions in the region where greater than 15 MeV electrons are present, it was sufficient to know that they can be a problem. We didn't need to know the exact fluxes. The Van Allen probe satellites have an instrument called REPT that may provide the measurements we need, but it's still going to take a lot of work to extract the correct values given the problems I just outlined above. Dr. Jeffrey Reeves specifically says that the reason the 1976 AE radiation belt model goes to 7 MeV is because they didn't have the capability to detect anything higher. This confirms that NASA has no way of knowing the electron energy fluxes of the area of the Van Allen radiation belt traversed by the Apollo missions, and as Reeves also pointed out, it's still going to take a lot of work to extract the correct values given the problems I outlined above. Another problem he mentions is Bremsstrahlung. As common sense would dictate, if spacecraft shielding is not enough to attenuate radiation to acceptable levels for the astronauts, then it follows that the Apollo astronauts would have been exposed to higher levels of radiation. However, on the flip side, too much metal shielding can produce X-rays which are just as harmful to astronauts, therefore also leading to an increase in the radiation count. The only way then to attenuate radiation levels to acceptable limits for the astronauts would be to have real-time data on the radiation belts on a consistent basis and then design spacecraft shielding accordingly, or more realistically, avoid these areas altogether. NASA did not have this real-time capability for collecting data on the radiation belts. As Gerard White points out, Browning tries to get as much mileage out of the 1976 AP8-AE8 radiation belt models as possible. Browning goes on to say that 0.1 MeV to 3 MeV electrons represents 99.95 of the outer electron belt along Apollo 11's trajectory, and that for all practical purposes, electrons greater than or equal to 6 MeV do not exist. As Browning says, according to credible sources, there are virtually no electrons above 14.7 MeV, which is convenient for his narrative since the claim is that the Apollo shielding can attenuate electrons up to 14.7 MeV. Who exactly are Browning's credible sources? 3, maybe 4 radiation belts. In the 1950s, the United States had launched into space a series of 3 nuclear warheads under the code name Operation Argus and detonated them below the Van Allen belts. The first warhead was launched August 27, 1958 to an altitude of 110 miles. The second warhead was launched August 30, 1958 to an altitude of 190 miles, and the third warhead was launched September 6, 1958 to an altitude of 493 miles. Each warhead had a yield of 1.5 kilotons and they were detonated over the South Atlantic Ocean. The kiloton yield in these warheads may not have been considered significant, yet it was determined that the X-rays from these explosions could penetrate spacecraft and disable electronics as well as cause radio noise. To make matters worse, this area includes the SAA, where the more intense inner proton belt dips to an approximate altitude of 100 miles. It was reported that after the detonation of these warheads, the Earth's ionosphere was temporarily disrupted. There were magnetic storms and disruptions in shortwave radio communication, and additional electrons were trapped in the magnetosphere, forming an artificial radiation belt comparable to the Van Allen belts in intensity. Sir Bernard Lovell, an English physicist and radio astronomer, was particularly concerned and said, regarding Operation Argus, that the scientists' results were somewhat alarming. So now, there are 3 radiation belts. NASA doesn't say exactly when this artificial radiation belt dissipated, but confirms that during the manned Mercury missions, it no longer existed. However, it can be inferred that it took at least 3 years for this radiation belt to disappear. However, by 1961, they were back to 2 radiation belts. There was also the launch of Operation Starfish Prime, another nuclear warhead. This was particularly troubling since this time they used a megaton bomb. This detonation was at least 1,000 times more powerful than the Argus bombs. It was launched July 8, 1962 and detonated 19 miles from Johnson Island in the Pacific Ocean at an altitude of 248 miles. On August the 20th, 1962, the Atomic Energy Commission, the Department of Defense, and NASA issued a report stating, "The solar cells of several satellites have been damaged. Measurements made in Peru calculated that the rate of radiant decay would be slow and 10% of the radio noise would still be present in 2 years' time. More than 100 trillion electrons from the fission product had been trapped by the Earth's magnetic field, which formed a new radiation belt at an altitude of 2,484 miles, with intensity over 100 times greater than the naturally existing radiation belts. The newly formed radiation belt was 400 miles wide and 4,000 miles deep, with a possible half-life of 20 years. Bennett and Percy write, "The length of a half-life is of paramount importance, as Professor John Davidson pointed out. Essentially, it continuously slows down, which means that the artificially induced radiation created by Starfish Prime would be dropped to half of its original quantity by 1982, by a quarter by 2002, to 1/8 by 2022, and that even by 2042, we would still be at 1/16 of the original amount of radiation. As the original dose was measured at 100 times in excess of the natural radiation levels, this means that by the end of this millennium, this artificial belt still contains a level that is descending from between 50 to 25 times the already intense background levels of the region of the Van Allen belts.